Welcome to the Forge College Explainer. So let's start with a problem literally every single developer on the planet faces at some point. It's that completely universal, mysterious amnesia that hits exactly 24 hours after writing a brilliant analysis script. You look at your own code and you think, who wrote this? What does this variable even mean? Now, in our previous lesson, Guided Hands-on Analysis, you were right in the trenches. You ran scripts, crunched the data, and produced some amazing visualizations for your Cloudbreak state storage evaluation. But right now, all that incredible work is basically just trapped on your local machine. Today's explainer is all about translating that localized chaos into a rigorous, reproducible engineering blueprint. We're diving into drafting technical documentation and findings. We're going to take your Solana capstone project and package it up so that anyone, anywhere, can run your code and get the exact same brilliant results you did. We are officially moving from, hey, it works on my laptop, to it works perfectly, every single time. And here is the undeniable proof. Here is our master schematic for today. We'll be covering 1. Translating analysis to output, 2. The 3 core sections, 3. The assembly line, and 4. The milestone quality check. Let's get right into it. Section 1. Translating analysis to output. Think of those raw metrics in RPC interactions you gathered as raw steel. Documenting your methods and findings right now is how you forge it, ensuring your draft is reproducible and technically rigorous. Your deliverables really aren't isolated islands. If you don't draft the actual blueprints now, that rigorous, genius work you did yesterday essentially turns into completely unusable scrap tomorrow. Section 2, the 3 core sections. Since we're engineers, we need to structure our documentation exactly like an engineering project. There are 3 core files you need, each with a very specific purpose and required elements. First up is methods.md. This is where you log your exact experimental steps, the commands, parameters, random seeds, all of that. Second is results.md, which is where you get to show off those gorgeous Cloudbreak visualizations, but crucially, tying them directly to your data inputs and evaluation mapping. And finally, the engine block, the repro instructions.md file located in your appendix. This houses the actual runnable scripts, manifests, and checksums. These 3 files basically form the holy trinity of reproducible research. And a huge part of this is data provenance. It's an absolutely crucial concept because strict data provenance is what actually protects your claims. We're talking about a strict record of every single input dataset source, its timestamp, and any filters you apply to ensure all claims are verifiable. What does that actually mean in practice? Well, it means knowing exactly where every single byte of your data came from. Without it, you're essentially handing a peer reviewer an IKEA furniture docs that's completely missing the instruction manual, and let's be honest, probably a few dowels too. You absolutely have to prove where your data was born. The difference between rigorous documentation and sloppy practices is pretty vast. It's the difference between a reproducible blueprint with beautifully pinned dependencies, exact version numbers, and maybe even a sleek container recipe, versus what I like to call trust me bro science. You know, where the inputs are missing and the only defense is, well, it worked on my machine yesterday. If that's your defense for a missing chart, your capstone project is for sure going to fail the audit. We want robust blueprints here, not broken promises. Moving on to Section 3, the assembly line. You really don't build a complex machine by just throwing parts in a room and hoping for the best, right? You follow a sequential assembly line. Step 1, inventory your artifacts. Step 2, draft the methods. Step 3, assemble the results. And Step 4, compose the appendices. It's a terminal sequence. Every single concrete step here needs to end with a get commit to lock it in. Once you finish a step, you commit it, and you move forward. Zooming in on that methods drafting step for a second, you must be incredibly explicit with your code blocks. You need to detail exactly how the environment was set up, data acquisition, pre-processing commands, analysis invocation, figure generation, and your parameters and random seeds. If you used a specific environment, write it down. If you ran a pre-processing command on your Solana RPC logs, put the exact terminal command in a code block. Sample the dataset with a random seed, document that exact seed. We want absolutely zero ambiguity here. Then over in your results section, think about the visualizations you generated. Whether you're working with time series plots, distribution histograms, or correlation matrices, every single one must be tied back to specific experimental conditions. And, more importantly, they have to tie back to the hypotheses you established way back in Lesson 1. Remember, A pretty chart is completely useless if it doesn't answer a specific question about Cloudbreak's storage efficiency. Now, think of your appendices as the actual engine room of your machine. This is where the real power lives. Your repo instructions.md file gives a third party everything they require to just flip the switch and rerun your end-to-end pipeline. It houses your dependency manifests so they have the right libraries, and most crucially, a wrapper script. Something like a simple run repro.sh file that executes the entire analysis from top to bottom with just a single terminal command. Which brings us to section 4, the milestone quality check. Okay, so you've built the blueprint and drafted the documents, but now we have to stress test the machine to ensure it actually turns on. We use a reproducibility checklist, which is a set of concrete, verifiable acceptance criteria. It ensures a single primary figure can be reproduced from raw data to the final image with zero manual intervention. This defines done for your capstone project increment. It completely removes any subjectivity from the peer review process. It's not about whether your reviewer likes your coding style, it's about whether they can push one single button and perfectly recreate your primary figure. If yes, you pass. If no, well, you've got a bit more work to do. So how do we actually run this check? You start by sanity running your runner script, doing an environment reproducibility check to build from the manifest, and running a data provenance verification using checksum validation. Executing these first 3 sanity checks in a completely fresh virtual environment is what guarantees your dependencies are pinned correctly and your data files match perfectly. And I really cannot stress the words fresh environment enough. Please don't run this on the machine you've been coding on for weeks. Spin up a brand new container or virtual environment to be absolutely sure. Finally, we have the last 2 checks: figure to command traceability and an evaluation mapping audit. You must prove that running a specific command block visually regenerates the exact figure. That's the traceability piece. Secondly, you have to audit your evaluation mapping. Does the result actually map explicitly to the evaluation criteria you set for Solana's state storage? Basically, does the data actually prove what you're claiming it proves? Because just generating a chart simply isn't enough. True traceability means explicitly explaining how that result references a precise hypothesis and supports or contradicts it. Contrast that with disconnected data, an orphaned chart just floating in your results document with absolutely no explanation of why it matters. That's confusing for the reader, and honestly, it really weakens your capstone. Every single image needs a job, and it needs to point back to your main thesis. The golden rule of scientific engineering is pretty simple. Clarity of methods means an independent reader can reconstruct what you did without asking follow-up questions. If a peer reviewer has to ping you on Discord or send you an email to ask how to run a script, your documentation just isn't finished yet. True clarity means your repository is entirely self-sufficient. It needs to speak for itself, loud and clear. So I leave you with this question. Is your capstone repository truly structured, testable, and ready for the ultimate peer review stress test? Now is the time to run your checks, finalize those Git commits, and lock in a rigorous draft. You've done the really hard analytical work. Now let's give it the presentation it deserves. Once you're completely confident in your repository, be sure to visit forge.college to learn more about advanced Web3 concepts, dive deeper into Solana's architecture, and further your journey with us. Keep building, keep documenting, and I'll see you in the next explainer.